Hey everyone, so we're going to continue our talk about the geophysical hazards in geography by looking at where a lot of these different geophysical hazards are located, including earthquakes, volcanoes, and mass movements. Again, this is going to be a consistent theme that we're going to be talking about these three particular types of geophysical hazards. So we're going to start off first with earthquakes, and earthquakes often happen along clearly defined linear patterns. The only uh, times where that does not happen is in the case of human-made earthquakes that we talked about. However, for most of the world's earthquakes, these are going to happen along these linear chains that follow plate boundaries, and that makes sense given what we know about earthquakes and why they occur. But there's two different types of earthquakes that we're going to talk about here. The first of them are broad belt earthquakes, and these are associated with subduction zones, right, where a oceanic plate plunges beneath a less dense continental plate, like we saw with the Boxing Day tsunami the other day. Um, and other, times where this happens are the Himalayas, where you also see that sort of collision boundary occur. There's also narrow belts of earthquakes, and these are with constructive plate boundaries, where the plates are moving away from each other and they construct new land. But the San Andreas Fault area in California is an example of these sort of narrow belts of earthquakes. Now, like I said before, human activity can cause isolated occurrences that do not necessarily occur on plate boundaries. And so that might be where we see some sort of outliers to this process. So here we see, where a lot of the different tectonic plate uh, earthquakes end up occurring. You can see there are some that are not occurring along the plate boundaries. However, the grand swath of them are happening along these plate boundaries. And you can see certain areas of the world where there's quite a lot of seismic activity, including Central Asia, Southeast Asia, the Middle East, and going into Eastern Europe, and then along places that we would think of in the United States, like California, the West Coast, and then the West Coast of South America as well. Now, in looking at volcanoes, most volcanoes are also found at plate boundaries, but there are some exceptions. And those exceptions are places called hotspots, where sort of plumes of heat escape from the mantle, and these are caused by the movement of these plates above the hot part of the mantle, sort of allowing some of this magma to reach the surface. And usually with hotspots, you sort of see land formed from these hotspots. The Hawaiian Islands are probably the best example of this because those islands were literally created by this sort of hotspot activity. And that's why, when I went to Hawaii myself, I was surprised by how many black beaches there were, but it's from this sort of volcanic activity that is happening within the hotspots that are leading to those shield volcanoes that you saw the other day and leading to some of the volcanic activity that still continues to take place and the formation of new islands over millions of years. But there are other hotspot areas. Iceland, the Caribbean, the Congo, all of these are hotspot areas where you can see sort of this non-plate boundary volcanic activity take place. However, most of the volcanoes in the world are along what is called the Pacific Ring of Fire. And the Pacific Ring of Fire is the border of the Pacific Ocean, following from the west coast of the North America, South America, and then the east coast of Asia and oceanic areas. 75% of the Earth's active volcanoes are along this ring of fire. And some of the world's most recent volcanoes, like Mount Pinatubo in the Philippines and Mount Unzen in Japan, and a couple others in Indonesia, Java, Mexico, Mount St. Helens in the United States. All of these are part of this ring of fire. And it is often caused by subduction in the oceans that provide these chains of uh, volcanic islands that are also known as island arcs. So the Aleutian Islands, which are in Alaska and sort of are the tail on Alaska, are an example of these sort of volcanic island chains. So where subduction of an oceanic crust occurs beneath the continental crust, you are going to see these sort of young mountains occur and these volcanoes sort of rise up. And so the Andes Mountains are another example of these, where there are several active volcanoes. Now, in terms of landslides, these are naturally occurring phenomena, and so you may think that they're more likely to happen everywhere, because there are a few things that are going to lead to these sort of landslides, but there are a few different traits of landslides that we can sort of follow. So this includes the fact that they're in temperate or sort of moderate climates, high latitudes, the ocean also has landslides, but the sort of fatal landslides that we may see that have the biggest impact on human populations tend to be more common in a couple different areas. One, places that have active tectonic processes. We talked about landslides as a secondary hazard for earthquakes the other day. You also see high levels of precipitation in areas where you have more landslides, so high annual rain totals, short-term intensities for these. You also have high population density because you tend to have more weight that is being placed on slopes. And so where one or two of these factors are absent, the risk of these sort of fatal landslides does become reduced because these are the three biggest. So in terms of these fatal landslides where a lot of these different characteristics may be in place, you are going to see them most likely in lower income countries where the sort of mitigation strategies, the infrastructure growth are less likely to be in place. So the southern edge of the Himalayas, central China, southwest India, the western boundary of the Philippine sea plate in places like Japan, which is not a lower income country, Taiwan, and the Philippines, central Indonesia, so again, Southeast Asia, and then the Caribbean and central Mexico, as well as the western edge of South and Central America, and especially in Colombia. So all of these places have a huge impact on where landslides occur. Now, another huge part of when we can expect and start to predict when hazards may occur or where they may occur is the idea of a recurrence interval. And this is known also as a return period. So this is the expected frequency of the occurrence measured in years for an event of a particular size. And there's a couple different rules with this. In general, small events are going to have a high frequency or a short return period. Large events are going to happen less frequently. So they're going to have a low frequency and a high return period because it's going to take more time for another one of these events to happen. So in essence, there are fewer highly destructive events, but many minor ones. The highest destructive events, those low frequency, again, high return period events, are going to cause the most damage and require the greatest management to make sure that there is a plan in place should one of these events end up happening. Now, in terms of looking at like tectonic activity, if you are over an 8 magnitude earthquake, that's going to happen about one time per year. Where these things happen and their impact on human populations is going to be variable depending on where they end up occurring. And then from there, a 7 magnitude earthquake has about 18 on average per year, so we can see that it continues increasing. A 6 is going to have about 120 per year. A 5 is going to have about 800 per year, and then continue to grow until there's about 49,000 3 magnitude quakes happening every year, where they are typically felt, but they usually do little damage depending on the area. Now, in terms of measuring earthquake frequency and sort of the magnitude, the things that we sort of talked about before, the most common scale traditionally has been the Richter scale, and this is used to measure magnitude of earthquakes. It was developed in the 1930s at the California Institute of Technology by Charles Richter, who the scale was named after. It is a logarithmic scale, so each scale is 10 times more powerful than the level lower than it. So a 3 magnitude earthquake is 10 times less powerful than a 4 magnitude earthquake. And a 3 magnitude earthquake is then 100 times less powerful than a 5 magnitude earthquake. So you can see that by the time we get up to like the 8s, that this is like thousands of times more powerful than like a 3 magnitude earthquake. However, more and more people, scientists I should say, are using the moment magnitude scale, which measures the amount of energy released and produces figures that are similar to the Richter scale. So for every increase of 1 on the M scale, the amount of energy released increases by over 30. And there's every increase of 0.2 is a doubling of the energy released. So a scale of 1 would be twice as less powerful, or half the power of half the energy released, I should say, of a 1.2 M scale, and so on and so forth. And then in terms of volcanoes, volcanoes are usually measured using the volcanic explosive index. This is based on a couple different factors: the amount of material ejected into the explosion, the height of the cloud that it creates, and then the amount of damage that is caused. So any explosion above level 5 is considered to be extremely large and violent, and then each level, just like the Richter scale, 10 times more powerful than the next lowest level. So a VEI of 7 is 10 times less powerful than a VEI 8, and that ejects more than 1,000 cubic kilometers of material. However, a good sign for us is that the last VEI 8 was about 74,000 years ago. However, as time goes on, given the recurrence interval, that could mean that we might have a more strong explosion to this degree, sooner than we think. All right, if you have any questions on this, please let me know. And again, we will continue talking about geophysical hazards going into the next section. Thank you.